Hello everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look to see how we can calculate the energy change that actually occurs in a reaction. So hopefully by the end of this lesson you'll be able to actually carry out those calculations successfully. Starts off though, we've got 3 questions based around our previous work, so have a go at answering those in your book for me first of all. I'll give you about 3 minutes to have a go at this. Let's check those answers then. So for question 1, it is an exothermic reaction, 1 mark for that. Question 2, hopefully we did draw a reaction profile like the one on the screen. So reactants line below the products line gets you 1 mark. And then if you had your little bump going above there, so joining those 2 lines with a little humpy bit, 2nd mark. And then if you'd labelled the energy change, you can have a bonus 3rd mark as well. But remember, it's got to go from the reactant line to the product line. If you labelled the activation energy as obviously the little bit that goes up to the hump, then you can have a bonus mark too. So 2 bonus marks available there. And then number 3, the minimum energy needed to start a reaction, that is our activation energy. So 1 mark for question 1, 1 mark for question 3, 2 official marks for question 2, but 2 bonus points available. So total of 4 for you there. Of course 6 with your bonus points. First thing we need to know then is what we're talking about when we see this phrase bond energy. So quite simply, the bond energy is the energy needed to break 1 mole of a particular bond. And it has the units of kilojoules per mole. Now, what I've given you in the table on the bottom left of your screen are a range of common bond energies. So we can see the bond on the left hand column and then the bond energy, so the amount of energy we need to break 1 mole of that bond on the right hand side. So looking at that table, what I want you to do after you've written the definition is see what conclusions you can draw about bond energies from looking at the table. There are 2 key patterns I'm hoping that you've picked out here. First of all, different bonds have different energies. So each time we can see there's a different bond, so different atoms joined together, we have a different bond energy. The second one is that if we have a look with the carbons, for example, so a carbon single bond carbon in that first row has a bond energy of 347, but by the time we're down to the carbon double bond carbon, about middle of the table there, that's 612 kilojoules per mole. And then when we come to the carbon triple bond carbon, the second one up from the bottom, then it's 837 kilojoules per mole. So the more bonds between the atoms, then the higher the bond energy will be. So in that table, we've obviously got bond energies, and those ones are actually mean bond energies. So what we've done is we've worked out the bond energies of those bonds in a number of different substances, and then we've taken the mean from that, and that's what we use in our table. But what you'll actually find is that if you carry out an experiment and you calculate the energy, then it could be slightly different. And I have seen this as a question previously, and if they ask you why it is that the values for the bond energy in a table would be different to experimental values, it's because the ones in a table are mean bond energies for the same bond in different substances. So we know the bond energy is the amount of energy needed to break 1 mole of any given bond. What I've given you are a selection of bond energies in the table, and you've got 4 questions to have a go at answering. Hopefully if you read the question and use a calculator, it shouldn't be too tricky to do. Definitely questions 1 and 2 should be very straightforward. Question 3 gets slightly trickier, and then question 4 is probably the most challenging. So see if you can have a go at answering those 4 in your books. Okay, so let's have a look to see how we solve these then. So for question 1, we've got 2 moles of carbon single bond carbon bonds. So the first thing we need to do is find the carbon single bond carbonate table, and we need to read off the energy there. And we see it's 347. Because we've got 2 moles of it, we need to do 2 times 347, which gives us 694 kilojoules. For number 2, we've got 5 moles of the oxygen double bond oxygen. So again, we find it, that's 498. So it's going to be 5 times 498, which gives us 2,490 kilojoules. For number 3, it's 2 moles of NH and 2 moles of carbon double bond oxygen. So we need to do 2 times our NH, which is 391. And then we need to add that to the 2 moles, so 2 times our carbon double bond oxygen, which is 805. So that gives us 2,392 kilojoules. For the last one, we've got 3 moles of methane forming, CH4. So the first thing to do is you need to work out what bonds there are. So it's easiest to draw the displayed formula. So methane looks like this. Then we can count up the bonds. So we've got 1, 2, 3, 4. So we've got 4 times the carbon-hydrogen bond. And if we look that value up in the table, it's 413. So we've got 4 times 413, and that is 1,652 kilojoules. Now, that's obviously for one of those moles, but we've got 3. So we need to do 3 times 1,652, and that gives us 4,956 kilojoules. So obviously 1 mark for each of the first ones you get. Then you can have 1 mark for getting the number of our bonds times by the bond energy for the first bit, so the 1,652, and another mark if you got the final one by timesing that by the number of moles. So you got a total out of 5 for that one. So we've worked out the amount of energy we'd need to either break or form any particular amount of bonds. But we need to go a little bit further to really grasp this concept. Because once we know the bond energies within any molecule, then we can actually calculate the energy changes in any reaction. So in order to do that, what we need is to work out the energy transferred from the surroundings to break the bonds in the reactants, and we'd need to use the energy transferred to the surroundings when new bonds are made in the products. So what we're doing is we're working out the amount of energy being transferred in our reactants as those bonds are broken, and then in the products as new bonds form. And from that we can then work out the total energy change in any given reaction. So jot those couple of points down in your book for me first of all. Before we go any further here, something we do need to remember are the valency rules. So this just tells us how many bonds different atoms can actually form. So the common ones are in the table here, and I'd suggest you make a note of these just to remind yourselves. So hydrogen can form a single bond, oxygen can form 2 bonds, carbon can form 4 bonds, the halogens, which are in group 7, can form 1 bond, and nitrogen can form 3 bonds. Now this is going to be really important for when we actually come to work out these particular calculations. So make sure you've got that little table jotted down. Those are the ones that are most likely to come up on any exam paper. What we're going to do then is go through an example together. So the type of question we've got is at the top. Calculate the energy change when ethene burns completely in oxygen. Depending on how nice they're being and the style of the question they've asked, they could give you a balanced equation, they could give you the displayed formulas for it, they could just give it to you in words. So you need to obviously be familiar with how to draw displayed formulas. If they don't give you the displayed formulas, step one is always drawing it out. Now in this case we've been given it, so we can see the displayed formulas for our reactants on the left and the products on the right. So the first thing we need to do is actually write down the number of bond of each type in the reactants. So we're just looking at the left hand side of the arrow. So from there, if we start off with the chemical on the far left, our ethene, then we can see in the middle we've got a carbon double bond carbon, and then we've got 4 carbon hydrogen bonds. So you can see we've written down there 1 times carbon double bond carbon plus 4 times the carbon single bond hydrogen. But it also reacts with oxygen, and we've got 3 moles of that, so it's 3 times the oxygen double bond oxygen. So jot this down first of all, and then we'll move on to step 2. Next thing we need to do is we substitute in the values for the bond energies from the table they will give you. You don't have to memorize them, don't worry. So all we can see there is in those brackets we've changed the names of the bonds for the energies. So 1 times 612, that's our carbon double bond carbon, plus 4 times 413, carbon hydrogen, plus 3 times 498, which is the oxygen double bond oxygen. Type all of that into your calculator and we end up with a value of 3,758 kilojoules. So that gives us the energy transferred to break all of the bonds. Now we need to repeat that process for our product, so on the right hand side of the arrow. So what we've got are 2 moles of carbon dioxide, so that's obviously in each carbon dioxide molecule 2 carbon double bond oxygens, so 2 times 2 gives us 4, and we've got 2 moles of water, and each water has 2 oxygen hydrogen bonds, so again 2 times 2 is 4, so we've got 4 times our carbon double bond oxygen plus 4 times our oxygen hydrogen. Same as we did before, we substitute in the actual bond energies from our table. So it will be 4 times 805, which is the carbon double bond oxygen energy, and 4 times 464, the oxygen hydrogen bond energy. Type that into your calculator and you'll get an answer of 5,076 kilojoules. The last thing we need to do is actually calculate the energy change. So we know the energy transferred to break the bonds, and we know the energy transferred when new bonds make, and then to work out the energy change, it's just the energy transferred to break the bonds in our reactants minus the energy transferred to make the new bonds in our products. So always reactants minus products. So in this case it's 3,758 minus 5,076. Put that into your calculator and you'll get the answer of minus 1,318 kilojoules. Now, whether it's positive or negative, it's really important that you show the sign, because if it's a positive value, that means it's an endothermic reaction. If it's a negative value, then it's an exothermic reaction. So the sign you've got to include. So let's just make sure we've got those couple of points about the sign written down, because it is really important and they can give you energy changes, either positives or negatives, and ask you what this shows. So negative sign is exothermic, positive sign, it's an endothermic reaction. What I've got for you here then are the 7 steps, if you like, to get this right every single time. So step 1, we draw out the displayed formula of all of the reactants and the products, showing all of the bonds. Step 2, we write out the bonds that have to be broken to convert the reactants into separate atoms. Step 3, we calculate the amount of energy that would take. Step 4, we write out the bonds that have to be made to convert the separate atoms into the products. 5 is we calculate the amount of energy that would take. 6, we work out the overall energy change because it's reactants minus products. And then finally we can state whether it's an endothermic or an exothermic reaction. So if you want to jot down those 7 points as almost a cheat sheet, if you like, of how to get this right each and every time, by all means do so. If obviously you've kind of got it already, then you don't have to write it down. So I'll leave this up for just another 30 seconds, but if you need longer to write it down, obviously hit pause and take as long as you need to do that. So what I've given you at the top then is the balanced symbol equation for another reaction. On the left, you've got the different bond energies that are relevant to this particular question. What I want you to do is have a go at working out the energy change for this reaction, remembering to state whether it's endo or exothermic at the end. Really important thing to remember about these kind of questions, because they're going to be worth at least 3 marks, is show your working. Write out each of those stages, because it's really easy to mess up, mistype a number, or just miss one bond out somewhere in your calculation. And if you've literally just written down an answer and nothing else, you've got 0. If you've shown all of your working and all you did was miswrite down what was on your calculator screen into the answer space, then you could still get all but that final mark. So always show your working. Have a go, work through those 7 stages, 1 step at a time for this particular question. So let's go through how to solve this then. First thing we need to do is draw out the displayed formulas for our reactants and our products. So C2H6, we start off with the carbons and they form the backbone, and then we will have the hydrogens attached. Now, if we remember, our valency for carbon was 4 and for hydrogen was 1. So if we look at each carbon, they've got 1, 2, 3, 4 bonds, whereas each hydrogen only 1. That's going to then join with our bromine, which is joined via a single bond to our Br2. And then our products, we've got C2H5Br. So again, start with the carbon backbone, put your bonds in place, and then you can fill out the hydrogens first, and then we can put our bromine on. The order of those doesn't matter in this one. And we've got HBr. So again, joined by a single bond because each has a valency of 1. So that's the displayed formula first of all. The next thing we need to do is work out what bonds we've got and how many of each. Now, all I'm going to do is I'm just going to divide the page into 2 for now, because we're going to look at the reactants first of all. So we've got 1 carbon-carbon bond, because if we have a look, then we can see that bit there is a carbon-carbon bond. So we've got 1 carbon-carbon. And we've then got these carbon-hydrogen bonds. Now we've got 1, 2, 3, 4, 5, 6 of those. So we've got 6 of the carbon-hydrogen bonds, and we've got 1 bromine-bromine bond. What we then do is we look at our bond energy table down here, and we're going to change the bond names for the energies. So we've got 1 carbon-carbon, so we don't need to write the 1 again, we can just put the energy because there's only 1 of them, so 3, 4, 7. Then we're going to add 6 of our carbon hydrogens, which is 6 times 413. And then we've got 1 bromine-bromine, which is 190. Type it into your calculator, and hopefully we would get an answer of 3015 kilojoules. We then do the exact same thing for our products. So we start off by working out how many of each bond we've got. So 1 carbon-carbon again. So we've got a carbon-carbon bond. We've got 1, 2, 3, 4, 5. So 5 carbon-hydrogen bonds and 1 carbon-bromine bond. And then we've got 1 hydrogen-bromine bond. All we now do is substitute in our values as we did before. So carbon-carbon is 347. We've got 5 of our carbon hydrogens, 413. Carbon-bromine is 285. And hydrogen-bromine is 362. So again, type into your calculator, add it all up, and hopefully we get 3059 kilojoules. So we now know the energy when the bonds are broken in the reactants and the energy when bonds are made in the products. All we then do to work out the actual energy transfer is our reactants minus our products. And that gives us an answer of minus 44 kilojoules. So because obviously it's the reactants minus the products every time, then the sign is important, because in this case it's a negative value. So that tells us this is an exothermic reaction, because we're giving out 44 kilojoules of energy, so it's going to heat up. Anytime we've got that negative sign, it's exothermic. If it was positive, it would be an endothermic reaction. So in terms of how you're going to get the marks, if you got your balanced equation then converted into the displayed formulas, have a mark for that. If you got your numbers of bonds on the reactants, a mark for those. Number of bonds for your products, a mark for those. substituting in, you can have a mark on each side again, working out the values, have a mark for each of those, and then your final answer and identifying it as exothermic. So that gives us a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. So give yourself a score out of 9. On your exam it won't be worth 9 marks, but it's good practice to then see how far you can get with getting the correct answer. Final thing for today then are the plenary questions. So have a go answering these in your books. I'll leave them up for about 3 minutes today, but as always, if you need longer, hit pause and take as long as you need.